What if the Big Bang never really happened the way we were taught? What if our universe isn't expanding into empty space, but is actually the inside of a giant black hole? Not science fiction, not metaphor. Actual peer-reviewed science is now exploring this possibility. A group of physicists has proposed a radical idea that the universe we live in emerged not from nothing, but from the collapse of an earlier universe into a black hole, and we are living inside it. Wild, right? But what makes this theory so compelling is how closely it aligns with what we already know about general relativity, quantum mechanics, and the mysterious dark energy driving cosmic expansion. Let's break this down and find out just how serious this theory is, and whether we really are living in a black hole. In Information, the Black Hole Universe Theory, an overview. This isn't the first time someone has proposed that the universe might be inside a black hole, but now there's a fresh take with some testable physics behind it. Black holes are bizarre objects, regions in space where gravity is so strong, not even light can escape. Inside, the laws of physics as we know them start to bend in strange ways. But here's the kicker. The internal structure of a black hole can, under certain conditions, look almost exactly like our expanding universe. How's that possible? Well, both the interior of a black hole and the fabric of our universe can be described using Einstein's general theory of relativity. When you model matter and energy in space, the equations allow for very similar behavior between a collapsing star forming a black hole and a universe expanding outward from a singular point. It's the direction of time and energy movement that changes. Collapse versus expansion. And that distinction might not even be observable from the inside. In here it says Einstein's equations explaining the similarity. And to understand this theory, we need to take a crash course in Einstein's general relativity. His famous equations describe how mass and energy shape the geometry of space and time. The more energy and matter you pack into a region, the more it warps the surrounding space. Now, physicists often simplify things by assuming a perfectly even distribution of energy across space. It's not exactly realistic. Nothing in the real world is truly uniform, but it works well enough for large-scale calculations, especially when modeling stars or the universe itself. When you model a star collapsing into a black hole, you're just cutting off that uniform energy at a certain radius and applying vacuum conditions outside it. In other words, it's like slicing out a sphere of dough with a cookie cutter and saying, "This is the star." Oddly enough, if you reverse the collapse and imagine the energy expanding instead, the math gives you something shockingly close to how we model the actual universe today. So what happens during a collapse? Let's imagine a star collapsing. According to classical general relativity, this leads to a singularity, a point of infinite density where the known laws of physics break down. But here's the thing, physicists don't really believe infinities exist in nature. They see them as signs that our theories have hit their limits. Quantum gravity, a still developing field that tries to merge quantum mechanics with gravity, suggests that at extreme densities, new forces or effects kick in. These would prevent matter from collapsing into a true singularity. Instead, the collapse would stall at a maximum density. And then something surprising could happen: expansion. This is the central idea of the black hole universe theory. What if that bounce from collapse to expansion is what gave birth to our universe? Big Bang or black hole bounce? The mainstream view is that the Big Bang marked the origin of everything, a spontaneous beginning of time and space. But this theory suggests that the Big Bang wasn't the beginning. It was the result of something else, the death of a previous universe. As matter collapses into a black hole, it reaches an ultra-dense state. If some unknown quantum effect stops the collapse and reverses it, it could initiate an explosive expansion. Sound familiar? That's basically how we describe the Big Bang. Only this time the explosion isn't from nothing, it's a rebound. So what looks like the birth of space and time might actually be the afterlife of an earlier cosmic structure. That's not just poetic, it's mathematically plausible. Fermions, pressure, and the Pauli principle. Here's where the recent research gets really technical. The paper argues that matter inside the black hole is mostly made up of fermions, particles like electrons and quarks, and fermions don't like to be crowded. Thanks to the Pauli exclusion principle, no two identical fermions can occupy the same quantum state in the same place. That's why electrons stack into orbitals around atoms, rather than all piling into one level. The researchers think that at ultra-high densities, this principle creates an enormous negative pressure, like a spring being compressed past its limit. That negative pressure causes a bounce, reversing the collapse into an expansion. In cosmology, negative pressure is associated with what we call dark energy, the force accelerating our universe's expansion. So this theory connects everything: black holes, quantum principles, the Big Bang, and even dark energy, by saying they're all part of the same process. Predicting the shape of the universe. Most people think the universe is flat. That's based on measurements of light from distant galaxies in the cosmic microwave background. But the black hole universe theory suggests that the space inside isn't perfectly flat, it's slightly curved. Imagine cutting a small circle from the surface of a giant sphere. That circle may look flat to us, but it still has a subtle curvature. If the universe is the inside of a black hole, then it has an outer boundary, and its geometry should eventually reflect that. Here's where it gets exciting. The theory makes a testable prediction. If our universe has a boundary and subtle curvature, that curvature should become detectable with better instruments and more precise measurements. In other words, we might be able to confirm or rule out this idea based on real data. Is this just math or real physics? Now comes the big question. Just because something works mathematically doesn't mean it's physically real. The exclusion principle does prevent the collapse of white dwarfs and neutron stars, but those can still form black holes when pressure exceeds a certain limit. So how could this principle save an entire universe from collapsing? The authors of the theory propose a new kind of exclusion principle, one that applies even at extreme densities. That's a bold claim. It's also a bit ad hoc, meaning it's added to make the theory work without a direct physical observation backing it up. Still, quantum gravity is largely uncharted territory. Many physicists believe something must intervene to prevent singularities, even if we don't know what that something is yet. So while speculative, the idea sits closer to serious science than many other fringe theories. How much of this is just nonsense? Let's be honest, science YouTube is full of flashy, misleading ideas. So where does this theory fall on the credibility scale? According to the narrator, this black hole universe idea scores a solid 5 out of 10 on the bullshit meter. That's not bad, actually. It's not pure science fiction. The math checks out. The theory aligns closely with existing models of cosmology. The only weak spot is the speculative nature of the new exclusion principle. So it's half speculation, half legit science. That's more than you can say for most dinner table physics debates. And next time someone says the universe came from nothing, you can drop this knowledge bomb. Actually, it might have come from collapsing hyperdense fermionic matter inside a black hole. That should end the conversation, or at least shift it. A universe that recycles itself? Let's stretch this idea even further. If black holes can spawn new universes, then every black hole in our universe might also be the seed of another universe. Think about that for a second. Every black hole could be a doorway to a new reality, hidden behind an event horizon, expanding on the other side beyond our reach. That would make our own universe not the beginning, but a middle chapter in an infinite cycle of cosmic evolution. This concept is called cosmological natural selection, or the fecund universe theory. Proposed by physicist Lee Smolin, it suggests that universes capable of producing many black holes are more likely to reproduce, leading to a kind of natural selection on a cosmic scale. Universes like ours, with just the right balance of gravity, matter, and energy, might be more fit in evolutionary terms. Why you should care, why should any of this matter to you? Because it changes the story of where we come from. It shifts the narrative from something spontaneous and unexplained to something cyclical and connected. If true, this idea means universes give birth to new universes through black holes, like cosmic Russian nesting dolls. It also reframes how we think about singularities, dark energy, and the shape of space. And it gives us something priceless in science, a testable prediction. That's how theories go from fringe to mainstream. Whether or not this theory holds up, it's a beautiful example of how science pushes boundaries. It dares to ask the biggest questions, and it reminds us that we're all still trying to understand the very place we live in.